Last week we taught you that there's a force of gravity that acts between any two objects with mass, and that force of gravity is exerted between, let's say, an apple and the Earth. It's also exerted between the sun and the Earth. It's at every level of the universe. Every two objects with mass exert an attractive force of gravity on one another. Now, Newton gave us an equation that describes that force of gravity. He said F is equal to big G m1 m2 over r squared. And we've spent a few days now solving problems involving gravity, including three object problems where we have, say, the Earth, the Moon, and the Sun. What's the net force on one of those three objects? But all this time, you've trusted me that there's a constant value G of 6.67 times 10 to the minus 11. I told you the very first day we started this that I would get to where that value came from. But for now, just trust me. Today, we're getting to where that value came from. A guy named Cavendish performed an experiment to determine the value of G. Remember, Newton gave us the equation, but Cavendish gave us the constant, the 6.67 value. Newton knew there needed to be a constant there. He just didn't know what that constant was. So Cavendish comes along and says, oh, I can figure out what that constant is by the following experiment. He called it the torsion balance experiment. It consisted of something that looks like this. We had a ceiling or the top of a box, something that I can hang a string from. And on the end of that string were two masses. We call this one mass 1, and we call this one mass 1. They're both the same mass. We don't want this thing to tip over. Mass 2 is going to come into play down here. We're going to bring mass 2 nearby one of the M1s, and we're going to get a force of attraction. That force of attraction is going to cause number 2 to go towards number 1, but also number 1 to go towards number 2. Now, Cavendish was able to measure a few things here. First of all, he's able to measure the value of M1. Got it. The value of M2. Got it. You can imagine how easy it would be to find the values of these masses. It would also be pretty easy to find the value of R, the distance that separates M1 and M2. What would be challenging is to find the value of F, the force. I want to take you to an analogy here to maybe help you understand this a little bit better. When's the last time you were on a swing set? Somebody says yesterday?
No, I was just kidding.
It's okay. I like going on a swing set sometimes. Not yesterday, but you get on that swing set. Everybody's done this, right? You get on a swing set and you twist it around. Okay, whether it was yesterday or whether it was last year or whether it was 10 years ago, you twist that swing set around, right? And then you let it go and you you spin faster, 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 right? You know what I'm talking about? You know intuitively that the more you twist it, the more force it requires to twist it. It's harder, right? The more you twist it, the harder it becomes. Otherwise, you just keep twisting and twisting and twisting forever, right? So you go faster and faster and faster. You know that it becomes harder to twist it. You know that it requires more force. If you wanted to, you could do an experiment or a series of experiments to determine how much force was required to twist that swing set certain distances or certain amounts. So maybe after you're done, you conclude that if I twist it a half a turn, it requires this much force, or if I twist it 3/4 of a turn, it requires that much force. You would know by experiment the torsional properties of that swing set, the twisting or the torsional properties of that swing set. Well, Cavendish would have known the torsional properties of that string. And then when he brings mass 2 nearby mass 1 and causes mass 1 to come towards mass 2, causes the string to twist, he would have measured the value of the force by looking at how much the string twisted. Does that make sense? Just like with the swing set, we have an intuitive notion as to how much force is being applied when we twisted a certain amount. He would know how much force was being applied by how much the string twisted. So now he knows the value of M1, M2, R, and F. And now all he has to do is take the equation that Newton already gave us, F is equal to G M1 M2 over R squared, and rearrange it to solve for G. Take the R squared up by multiplying, F times R squared, divided by M1 times M2. And when he did that, he would have gotten the value of 6.67 times 10 to the minus 11. Units would be Well, they're on your data sheet, and we've given them to you already, but I'll show you where they came from here now. F is in newtons. R squared is in meters squared. Kilograms times kilograms, or kilograms squared. So, by bringing one mass near another and measuring how much the string twists, he was able to determine the gravitational constant that Newton didn't know. It was 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared. Is that okay? Make sense? Where are you going to see a question like this? Like if you see a question on Cavendish's torsion balance experiment, where are you going to see it on your test? It's going to be in the multiple choice, right? Right? You're not going to get a question that you're asked to solve for something mathematically with this or describe something in a paragraph. If you see something like this, it's going to be in multiple choice, right? You know from your previous two tests that that's the kind of thing you tend to see. Not so much. Sometimes little calculations, but not so much calculations. It's more qualitative stuff. Newton's laws, Cavendish's torsion balance experiment.